Dmitri Nikshych, and he will keep telling us about braided fusion categories.
Thank you. Good afternoon. So today we'll talk about group actions on braided categories, and equivalentization and de-equivalentization. There are two procedures, mutually inverse, and I'll define them and explain what one can do with them. So let's set up things. So let A be a fusion category. Its tensor are at equivalences. So let me define. So a tensor at the equivalence of A is an equivalence with additional structure that respects the tensor product. So I think I did not write it completely. So what's the additional structure? Additional structure is a natural collection of isomorphisms, f of the product and the product of images of f. Let's give it a name. I'll call it, what's a good name for it? Let's say comma y. Okay, so this structure is to satisfy certain compatibility. Remember, all these natural isomorphisms, these coherence constraints that we introduced, they're to satisfy something, right? So we can explain what they have to satisfy here. So there will be a diagram like this, which is composed from this tensor structure on F and associativity constraints. So let me write this down quickly. Okay, so what are the arrows? So here the arrow is associativity constraint, right? Because what happens here in the right vertical arrow that we are shifting a parenthesis. So here it's F applied to the associativity constraint of the category, and the horizontal arrows are this tensor instances of this tensor structure, right? So this will be what Fxy. This will be no, it will be Px yz. This will be phi xy. This will be phi y. Sorry, xyz, phi yz. Okay, so this is the coherence condition. So that makes it a tensor at equivalence. Now, what do tensor at equivalences form? They can be composed. So, under the composition, they form a monoidal category. So, like this O tensor of C.
So I'm assuming that f of 1 is 1, or naturally isomorphic.
Yeah, I always miss this, right? So, yeah, this is a part of the definition. So, there is also an isomorphism between F1 and 1, and it satisfies certain coherence, which is easy to write down. Okay, so this is the essence of this is the main thing. So this is a monoidal category under the composition. So it's clear that composition of at equivalences is at equivalence. One can define the tensor structure on the composition that would satisfy this diagram. So it's not just a monoidal category, but in fact, it has additional property, right? Because we deal with the equivalences that every object here is invertible. Yes?
Okay.
So such things are called categorical groups. So I'd like to stress, because in the beginning, on Monday, I said that we are going to consider linear categories, etc. This is an exception of this. Of course, this is not linear, right? The sum of two such functors is not going to be a tensor functor, right? So we only have composition, not direct sum. So this is a categorical group. Now, if I see, I'm sorry, I called it A. All right. So if A is braided, in addition, then we consider braided at equivalences. At equivalences, well, this will be at equivalences with additional property. Okay, they have to be compatible with the braiding. So let us try to express what property they should satisfy. So let's see. such an equivalence, right, should behave well with respect to the braiding, right? So here, if you apply F to the braiding, and then we can apply monoidal tensor structure, right? So here it will be phi xy, here phi yx. You get phi x fx tensor fy, fy tensor fx, and this would be the braiding cfx fy. Let's just compare this to the vertical arrows, right? So this and this. It expresses the idea that F preserves braiding, right? You need the horizontal arrows. You need vertical arrows to to complete the diagram. So my point is that you don't really need to remember any diagrams. I certainly don't. But each time you want to express a coherence, there's only one meaningful way to do so. Okay, so now these groups can be computed in concrete situations. So for instance, if A is the category of G-graded vector spaces, and then the group of tensor equivalences of A would be the semi-direct product of the second of the Schur multiplier and the group of automorphisms of G. A braided example, let's take a braided category. Let's take the CAQ. Remember, it shows up every lecture. It's a typical example of a pointed braided fusion category. So it's a group of braided equivalences is the orthogonal group. The group of automorphisms of A that preserves this quadratic form Q. So when I say this, let's compute a group, of course, I'm just computing the underlying group. It's more than just a group, it's a categorical group, but I'm saying nothing about associator here. So let's try to use this board now. So I mentioned the group action. So we said an action. From now on, let's switch to braided categories. I mean, there is a story which is non-braided. I will not need it. So now let's see the braided fusion category. And let G be a finite group. Finite because we want to get a finite category at the end. So then an action of G on C is a monoidal functor, categorical groups. Now we can view G as a very boring categorical group. So all the morphisms are going to be identity morphisms. So the only thing that matters is the tensor product. So it's a monoidal functor from G to the group of braided. How did I denote it? Of braided equivalences of. So what it means? It means that that for every G, let's give this a name. Let's call it I don't know, say yeah. So to any G, we assign an equivalence of G, and for any pair of elements of a group, we have an natural isomorphism of tensor functors. Let's call it like gamma GH. Let's call it maybe phi to be consistent with previous notation, where this thing would satisfy the same diagram that I had in the beginning, right? So if you have like 3 elements of a group, then you will be able to draw such diagram, and that these phis have to satisfy. Okay, so what this means is that it's more than just a homomorphism from G to the orthogonal group. It's homomorphism with some extra conditions, some extra coherence. Okay, so now what can we do with such an action? So we can form a new category. So here is an analogy, classical analogy. If you have a group acting on an algebra, you can form a fixed point algebra, right? G acts on an algebra A, so we can form fixed point subalgebra. Denoted usually like this, A sub G, all the elements of A that are fixed by G. Now, in the categorical world, we don't fix things, right? We fix them only up to isomorphism. So this motivates the following definition. So in this setting, so and a G equivariant object in C, where C comes with the section that I described, is a pair. Is a pair consisting of what? An object X in C and a natural family of isomorphisms, which I denote UG, between the image of X under the equivalence FG and X itself. Okay, so the fixed condition is now replaced by existence of such an isomorphism, right? Again, it's totally in the spirit of what we are doing, right? We're trying to be consistent. We do not require things to be equal, but rather are isomorphic. Now, and then again, once you introduce a natural isomorphism, it has to satisfy something, right? Well, it should be clear what it should satisfy, because you see, like this isomorphism should be compatible with the product in G, right? So let's draw a diagram. So what we'd like to have, this is okay. Now this is not okay. This cannot be moved. Okay, I'll draw a diagram. Okay, I'll squeeze it here. So if you have like this FG, FH, X, then we can apply UGH to X, or you can apply, you know, that in two steps. You can apply first. Can you see it from the? Okay. I'll reproduce it here. So you first apply FG applied to UH and then UG. So here I write this down. So what we have is that UGH should be equal to the composition of UG and FG UH, sort of a Banca cycle condition, right?
Mhm.
Okay. All right. Say again?
On the left-hand side would be the phi G.
All right. Okay. So you are right. Yes. So let me. Okay. So it's very good that people are following me and corrected with some of my mistakes. So this. Okay. So the correct diagram would be this. So this is phi GH, right? F GH X X, and that now we apply.
I think that the top shouldn't be UGH. It should be UGH in the bottom, right? Because UGH doesn't go. It needs to go from FGH, right?
Correct again. Yes. All right. So let's see. That's what happens when I try to skip things. But let's do it right. So FGH, correct. So FG FHX X UGH. So this is X. This is phi GH. This is FG of UH, right? So this is FGX, and this is UG, right? With the third attempt, we succeeded together. Okay, so all right. Now, so well, again, equivalent objects can be tensors. So there is a tensor product of equivalent objects, and so we have CG, the category of G equivalent objects in C is in fact a tensor category. Okay. So one can check, you know, that this tensor product admits associativity constraint. In fact, it's a fusion category, but it's actually even more than that, because we never used so far the fact that this action on of G on C by braided at equivalences, right? And the definition, it was a braided action, And because of this, this equivalent category CG inherits the braiding from C. So CG inherits the braiding from C. So what I mean by that, if you have a pair of equivalent objects, X, U, and say X prime, U prime, where X is an object of C and U is the equivalent structure, then the braiding of CX and X prime is, well, it should be, of course, a morphism from X tensor X prime to X prime tensor X, but in fact, it's a morphism in the equivalent category. So again, you can guess that the morphism in the equivalent category is something that commutes with the equivalent structure, right? Again, I would probably need to draw like, another couple of diagrams, but as you see, I'm not very good at it. Okay, so I'll leave it as an exercise then.
So the equivariance is really a structure, right? So not unique.
No, not unique. Like, so we will talk about this, right? So this U can be chosen in many ways. So again, a particular X can have several equivalent structures or none at all. Okay, so conclusion of all this. So conclusion, the equivalent category CG is a braided fusion category. Okay, now let's look at some examples to make it less mysterious. So the simplest category of all is the category of vector spaces, right? Well, that's a trivial category, and that's how it is called, and rightly so.
What is X tensor U?
Again,
You wrote X tensor U.
Yeah, it should be.
almost. Okay, so now, so let's consider example. So first, consider an action of G on the category of vector spaces. Well, this necessarily is a trivial action, right? Such any because vec G only has trivial equivalence. It's right that map like one-dimensional space to one-dimensional space, right? Okay, so let us now, but still, it's an action, and we can form equivalentization like this, right? What it consists of? Well, by definition, its objects are pairs V and this collection UG, right? Vector space along with what? This collection of isomorphisms UG from V to V. Now, the diagram that we wrote here tells you that this map UG is a representation of the group G, right? It has to be multiplicative. Representation of G. I mean, F is trivial, this is trivial, so you are left with UGH equal UH. Yes, okay? So the conclusion, therefore, that this equivalentization is just the category of representations of G. You see, well, not so bad, right? If you start with the trivial category and produce something less trivial. Next example. Now, let's consider the category vec sub G, which, if you remember, was the category of G-graded vector spaces. Now, there is an action of G by the equivalences, namely G can act by conjugation, meaning that the G sends the homogeneous space, the vector space supported on a component X to the vector space on Gx G minus 1. So it shifts permutes the components of the gradient, right? It's an action, and you can form the equivalentized category. So we have G, well, again, you can figure out what it is. So elements of vec G are vector bundles on G, right? So these things are equivalent vector bundles. I said this words before, so this is the center of vec G. Again, something non-trivial.
Dmitri, one question here. And if you change vec G by vec G omega, how much change?
You put omega star.
You get an omega everywhere. Okay.
Okay.
I have a question. We you define this for braided Fusion category, but vector G great vector spaces, it's not going to be braided if G
That's
is not.
correct. Yeah, so, well, I sort of defined it for all the categories, right? Because like this
Makes sense.
definition of a fusion category didn't require braiding.
I see.
In the presence of braiding, you get braided category. In
Got it.
absence,
Thank you.
get- Yeah. Good point.
Oh, okay. If you have an outer automorphism of the group, what do you get? Not an inner one. Can you do that? The same thing?
Well, you don't need. Well, what you need is like a map from G to the group of automorphisms, right?
Yeah,
So, well, there is kind of a natural map for a sense each element by
yeah, but if you
conjugation.
put an outer automorphism
Well,
there
you get
in the
some
group-
other category.
Oh, no, because it's the center is like something very non-trivial.
I mean, so each time you have an action, you have a quantization. And I agree that there are many possible actions.
Okay,
There are many possible answers.
oh, okay.
All right. Okay. Yes. So what was I saying? Okay. Yeah. Okay. So now this analogy that I mentioned in the beginning with fixed point subalgebra is again has to be taken cautiously because what we now have, of course, CG, the equivalent category is not a subcategory of C. Its objects have different nature. What you have instead, however, is a forgetful functor that ascends a pair xu to x that forgets the equivalent structure. Right?
It's
So
C,
it's-
no, not C.
So it's rather a quotient of the category, not a subcategory. Also, the Frobenius-Perron dimension of the equivalentization is the bigger than the Frobenius-Perron dimension of the original category. It's the order of G times the original Frobenius-Perron dimension. Okay. So now, let's make an observation. You see, like inside the category C, there is a category of vector spaces, right? Namely, it consists of all the multiples of the identity object. Now, the action of G, of course, preserves the subcategory, right? It maps this, unit object to itself. So because of this, what we have that equivalentization of F sits inside the equivalentization of CG. But this is the category of representation we just saw. So we have that. Well, furthermore, so it consists of all these objects xu, where x is equal to 1. Now, 1 centralizes every object in the category. Yes? So this subcategory, therefore, it's not just a subcategory, it's a subcategory of the symmetric center. Rep G sits inside the symmetric center. So in particular, the result will not be non-degenerate if you start with a non-trivial group. There always will be a symmetric a part in the symmetric center. So what did we establish? So let us record our construction. So we started with braided fusion category with an action of G. What fusion category? Let's say with that. With an action of G. What we obtained braided fusion category, a copy of the Tanakian category Rep G in its symmetric center. Is it clear what I mean? Right? So we started, so this passage goes like this. We start with C, we assign the equivalentization CG. So now the action, so what did we get? We get a larger category, right? And this category does remember the action. The way it remembers it, it contains the Tanakian subcategory inside the symmetric center. Make sense? Okay, well, it turns out that that's a two-way street. Okay, so there is an opposite construction. So this construction is called equivalentization. And can you guess the name of the opposite construction? Yes, very good. So de-equivalentization. Yes. All right. So let me explain that. Okay. So. Yes.
But we can get the modular category out of this. Question is, this is after this G quantization, we don't have modular because we have a center.
That's right, yeah. So,
When we
we-
put motion, like, when we
yes.
quotient it, it's.
Okay, so I'm going to talk about this. All right, so this de-equivalentization, that's what it does. So de-equivalentization kind of tries to kill, the symmetric center, try to turn category into a modular category when possible. All right. Okay, so all right, so let's see. So let's talk about de-equivalentization. So the setup is the same as like on the right hand side of this diagram. So now let's say D be a braided category with I call it E, the Panachian category of representations of a group G, then sits inside the symmetric center of G. All right. So what we want to do is somehow to cancel this part. All right. So here's how we're going to do it. We have an algebra of functions on G. Now, this is not just an algebra. This is an algebra with an action of G, right? So G acts by, say, right translations. Yes. So we have an algebra. Okay, so an algebra with G action that preserves its product. Let me give it a shorter name. I call it like A7. Is an algebra. In fact, it's a commutative algebra in rep G and therefore in D. Now, I should explain what I mean by commutative. Well, how do you define commutativity for the usual algebra? So if you switch the arguments, right, multiplication does not change, right? Well, in the presence of the braiding, you can switch the arguments, right? Let's say if M is the multiplication of the algebra, you can do this. You can apply the braiding, which permutes A with itself, right? And apply multiplication to the result. So if it does not change, then we say that the algebra is commutative.
I have a question. So this AG is an object in rep G.
It's an object with additional structure.
Okay,
It has
because the way it looks like you wrote it looks like it was like us. Okay, cool.
Yeah. No, I mean, I'm serious when I say that I appreciate all the corrections, okay, because you see, like they grow exponentially with every lecture. So yes. Yes, so it's a commutative algebra. And so what can we do with an algebra? Well, we can take modules over it, right? So then let C sub A G be the category of AG modules, not C, I call it D, like D sub AG, of A modules in D. Okay, again, a module is a module, right? It's an object along with the morphism, like this AG tensor M to M that satisfies the usual associativity that module action satisfies. Okay, now, because as is well known, modules over commutative algebra can be tensor, right? So this DAG is in fact, so the AG modules have tensor product over A. Again, you define tensor product over A as you usually do by universal property. It's going to be certain equalizer. So if you know how to do this, like in graduate algebra, you know how to do it here. And so as a result, we conclude that this category is a tensor category, in fact, a fusion category. So I necessarily skip some things, because what you need to do is to explain several things which I don't do. So you have to explain why this is semi-simple, right? Why there is duality. Yes. All this holds, and it's not hard, but it would require things. So the fact is, the semi-simplicity is due to the fact that that's a semi-simple algebra. Okay, so it's a fusion category, but in fact there is more to that. Look, what we did in the process. The only thing that we used was that this algebra is commutative, right? Now, it would be commutative if rep G sat inside D, right? I would say the same words and I would be correct. But in fact, more is given. Not only it's inside D, it's in the symmetric center of. Now, this allows you to introduce braiding on modules. So since AG is contained in the symmetric center, we are, so this category inherits the braiding from D. In other words, you have two modules where you have the braiding in the category D, and the statement is that this braiding actually commutes with the action of the algebra. So it's a morphism of modules. So finally, note that the group G acts on this algebra of functions on G. That's how we started actually, right? It acts on it by right translation. But you see, like if you have a group acting on an algebra, then it acts on the modules over this algebra, right? You have a module action, you twist by this action on an algebra, right? You get a new module. This results into the action of, so from here, we get an action on AG modules. Okay, and so what we get at the end of the day, did we construct? So we constructed this category D sub AG, and what kind of category is that? So it's a braided fusion category, with an action of G. I just explained where this action comes from, right? It acts on an algebra, and so you have action on modules over this algebra. Well, that's precisely what we were looking for, right? So we started with a category of this sort, having a Tanakian category rep G inside its symmetric center. And then this dequantization does what? It sends D to this D sub AG, like that. Yeah. Now, two constructions in the opposite direction. In the opposite directions, it turns out they're inverses of each other. The names suggest, right? It should be like this. So, meaning that if you apply equivalentization first and then followed by the equivalentization, then you get the original here. Okay, so if you start, let's see, so how can we go? We can start with C, form equivalentization, and then apply the equivalentization. The result is an equivalent, canonically equivalent to C. And in the opposite direction, if you start with D, form the category of modules, and then equivalentize it, well, you recover D again. So these are inverses of each other. Okay, so that's very good. So now, what's the lesson here? Because of the question that was asked. So de-equivalentization allows you to mod out by Tanakian subcategories in the symmetric center, right? So de-equivalentization allows to mod out by Tanakian subcategories in the symmetric center. Okay, so let's see how far we can push this. So I'll talk now about this, and it was supposed to be the main notion of today's lecture, namely the notion of the core of a braided category. So the core of a braided fusion category. And the idea behind this is that you want to separate the part of the category that comes from finite groups and leave a truly interesting, part. Idea is to separate the part that comes from finite groups. Oh, this is not rather informal because I didn't specify what exactly I'm planning to do. But let me do it now. So we start with a category C, with braided C. And let now,
Won't be able to do it on.
yeah, I mean, that's true. I wouldn't be able to move it, but I mean, one of them kind of keeps falling, which is not so good either. Well, anyways, okay, I'll do this. Yeah. Okay, so Start with a braided fusion category C, not necessarily non-degenerate, arbitrary braided fusion category. Suppose now take a Tannakian category. In fact, I'm going to do this. I will take a maximum Tannakian subcategory E sitting inside C. So maxima with respect to inclusion. So it's not contained in any, it's not properly contained in any larger Tannakian category, right? So it is a maxima. There can be several, even corresponding to different groups. Yes. So pick one of them. Now, we do not require, so not necessarily in the symmetric center. I mean, if it were in symmetric center where we knew what to do, we'll take the equivalentization. But what we can now do, so now take it centralizer. Take the centralizer. So it's a collection of all the, it's a subcategory of all the objects in C that centralize objects in E, right? So by definition, E is certainly contained in a prime, but it's contained in the symmetric center of a prime naturally, right? Because things in E centralize everything in E prime, right? So now we can perform the equivalentization in this setting, right? So can the equivalent, let's you see, that's the word, variantize. It would be a good word for the following purpose. So when I go to a pub and I want to know, where I should stop and go home, I should try to pronounce the equivalentization. And this way, I will know that it's a time. So can the equivalentize E prime by E, right? So now the notation that we used for this, it was kind of well, anyway. So what would that be? So we form this E prime sub AG. Okay. And now, which is now a braided category, is a braided fusion category with an action of G on it. Okay, now and a theorem related to this. So first of all, before I state a theorem, let me explain what's the linear algebra analog of this. It's actually very simple. So we always try to illustrate such things with an example, with examples involving quadratic forms. So now let's take C to be CAQ, where A is a abelian group and Q is a quadratic form, right? Multiplicative quadratic form. So let I call it like this, E inside A be an isotropic subgroup. By isotropic, I mean that Q restricts trivially to this subgroup. Okay. So then, well, E is contained inside its orthogonal complement, right? And we can form the quotient. Now, well, I mean, of course, we can take quotient of anything by anything in the abelian group. But now this thing admits a quadratic form. This form Q descends on this quotient because it's trivial on E, and it's orthogonal. Quadratic form Q tilde here. Okay. So now you should see how this construction is parallel, right? So this is the equivalentization that we formed, like this ugly notation here is this thing, right? Okay, so this is the essence of it, right? Once you start thinking about it in this way, all that you do seems very natural. Okay, so so I put it like this. So C E orthogonal by E Q tilde is the like this E prime AG above. So it would correspond to this. Okay, now the theorem that I wanted to state is that this construction, again, look, what I didn't require maximality up to this point, right? So if I admit that E is maximal, I will still be able to do all these things, right? It was never used. But maximality is important for the following reasons. So theorem, the equivalence class of this category E prime sub AG does not depend on the choice on the choice of P, of maximal Tanakian. There is a linear algebra analog of this, which you can find like in textbooks on linear algebra. That's same here. Like if this E is maximal isotropic, then this thing does not depend on any choices. So it is an invariant. So we call this. So technically, it's not just one category, but rather a class. So we pick a representative of this class. We call this the core of C and denote core of C like this. So in fact, a little bit more is true. You see, like this core well, I'd say
I have a quick question.
I'll make comments. Yes.
Is the core non-degenerate?
Not always, but very close to being non-degenerate. Okay. So let me explain. So yeah, so since this question arises, why don't I answer it right away? So notes. Okay, so first of all, if C were non-degenerate, then core will be non-degenerate. Second, the maximality of the things by which we quotient implies the following. So the core of C is name is called weakly. I'm going to define what it means. Weakly anisotropic. There's no Tanakian, no non-trivial Tanakian subcategories invariant under the group of its braided at equivalence. So what it means? It can have Tanakian subcategories, but not invariant under this. Okay. The reason for this is that there is a correspondence between Tanakian subcategories containing E and invariant subcategories of this core. Right, that's how it works. This is kind of the latest isomorphism, in group theory. So here you have to take the the invariant subcategories. Now, what it means? Well, that's actually quite a restrictive condition, because it implies immediately that the symmetric center of the core, let's see, like I said, it can be degenerate, but the symmetric center is either vector spaces or supervector spaces. So that's what I meant when I said that it's either degenerate or very close to being degenerate, okay? And the reason for this is simple. So you see, if we know that the symmetric center by Deline's theorem has a very specific form. So for any category whatsoever, and in particular for that core, the symmetric center will be rep GZ by Deline's theorem. So remember what it was. It's like representations of G, and the braiding is twisted by this element Z, right? But you see, this category would contain a Tanakian subcategory, rep G mod Z. So here, the order of Z is 2. And you see, this is the unique maximal Tanakian subcategory here. As such, it is invariant under auto-equivalences, right? Symmetric center is invariant, yes? So its largest Tanakian subcategory is invariant, yes? And so this has to be, so this has to be trivial. So which forces it to be either vector spaces or supervector spaces. The order of this is at most 2.
Don't you require a fiber function to have this linear theory? Do these all categories have fiber function?
Well, it is true, of course, that for this category, there is a fiber function of the category of supervector spaces. That's in fact a characterization of a.
Yeah, but the symmetric core, how do you know? I mean, how do you know you have a fiber function in the symmetric center of the.
Okay, so just to make things clear, like for what I said, I'm not using fiber functions. Okay, so what I have is a symmetric category like this. And by Deline's theorem, it looks like this. Now, what you said is true, that symmetric fusion categories are characterized by the existence of a symmetric fiber function, which goes in either to the category of vector spaces or supervector spaces. All of this is true. Okay. Yeah. All right. So, yes. So, and you see, like if your symmetric center is the category of supervector spaces, then well, unfortunately or fortunately, there is not nothing else that you can do. You cannot really kill this, category of supervector spaces. You have to live with this situation. So such categories are called slightly degenerate definition. If a symmetric center of C is supervector spaces, C is called slightly degenerate. The conclusion is that, to say it in other words, that the core is either degenerate or slightly degenerate. So it's as close as it gets to non-degenerate fit. Okay. So, and this is what I meant when I said that we are going to separate the part that comes from finite groups, right? So inside the core, there are, well, okay, I should say like one final thing. So in principle, you can repeat this procedure. You can take the core and form the core. It should still be possible and give something non-trivial because you see like there can be still Tannakian categories inside. They're not going to be invariant, but they're Tannakian. But this is not going to continue. So the third core coincides with the second, so it stabilizes very quickly. Okay. So in other words, the second core is something that we would say completely anisotropic. So it will have not Tannakian subcategories at all. Okay. So so my next my plan for the next lecture, just a second, so
Yes, sir.
would be to kind of go in the opposite direction, how, like, let's say if you know what the core of the category looks like, how can we reconstruct the whole category out of this? Okay, so this procedure is called gauging. That's I'll talk about tomorrow in the morning.
Comments or questions for Dmitri? Okay, I did have a question and then. So what are examples if you have in mind of completely anisotropic? I mean, families of
there are, well, okay, so for instance, you can take, like the group like Z mod P and take any non-trivial quadratic form, right? So the radical is going to be trivial, yes. Or let's say take, I don't know, let's say F take the, the orthogonal, let's say take this and take this non-degenerate symmetric form, right? So, inside this vector space within our product, there are no invariant subspaces. Orthogonal group is too large and it would permute one-dimensional, would extransitive on one-dimensional isotropic subspace.
And these are all pointed. Do you have non-pointed?
Yeah, like just take, I mean, like all those categories that come from affine Lie algebras and quantum groups, they typically have not Tannakian subcategories at all. So they're just strictly or completely anisotropic. So, like basically, and there are plenty of things like this. So each time when you have a category without Tannakians, which then you get this, and so just to make it clear, the group theory covers only small part of this. Okay, so the interesting things start to happen, once groups are gone, and I hope to be able to talk about that as well.
One more question about the groups. So we saw that groups generated lots of nice, easy examples through RepG and the symmetric center and stuff like that. And you're working hard now to get rid of the groups.
Yeah.
But I was also wondering, does any of this teach you anything new about groups? Can you learn anything new about representation theory from this?
Oh, hard to say. I mean, it's not, well, nothing of the sort, that would help like the classification of simple groups, but it does tell you that, certain groups act on interesting things, for instance, which I have not seen, like in the classical, in the classical situation. So you see, like you can associate with a braided category like a certain Grassmannians, it's consisting, let's say, of Lagrangian algebras inside. And these are acted upon by groups of autoequivalences. So you can study those and they produce interesting results. Yes, Hector.
Yeah. When you have the symmetric center of the core of C, but now you work in positive characteristic, do you know what it is? Is it Ver P or is always vec or super vec? Because I don't think you have the links theorem in positive
No,
characteristics?
I don't actually. I don't think you can pull, just play this game in positive characteristic, because here we use the algebra of functions, right? And use the fact that it's semi-simple.
Ah,
It's no longer going to be the case in positive characteristic, and I seriously doubt it's possible.
okay.
Yeah, I mean, of course, there is like this huge activity about asymmetric categories and characteristic C, but whether this construction goes through, I don't know. I mean, it does really depend on this, on the Tanakian, subcategories RebG. So Devin's theorem does not hold this way in positive
Yeah.
characteristic.
That's why I think
So
maybe
I
that-
don't really know
Okay,
what happens there.
okay, thank you.
Probably not.
Other comments or questions?
There
Oh,
is.
sorry.
So this might be really basic, but is it possible to sort of go through how all of this core technology works for a really easy example, like the Ising category or something like that? Sort of Z2.
Well, the Ising category, unfortunately, Ising category is its own core. And the reason for this is there is nothing Tanakian inside the Ising. So there is a category of supervector spaces that sits inside, but that's not Tanakian. What you can do, well, you can say, I mean, it's interesting that you consider Isings to be like basics. Well, they probably are, but you can do well. I give this example, pointed, which was supposed to convince people. But what you can do, for instance, you can take like Ising tensor Ising, and this would contain like a SVEC tensor SVEC inside. So which is a symmetric category of dimension 4, and this would contain RebZ2 inside. Just take the product of two fermions. Okay, so then you can do this. Okay, and the core of this Ising tensor Ising. What would that be? I think it will be. I think it will be pointed category, something like I think the center of vec Z2. Okay, and then if you do this again, you kind of, like if you take the second core, you get the category of vector spaces. So which kind of shows you that Ising is really built from groups, despite the fact that there is an object of the square root of 2. Okay. Does this help at all?
Yeah, it does. I mean, ultimately, I'd like to figure out what this core means in a vertex algebra setting. And so,
Oh, that would be
I'm
interesting.
picking examples which,
it should mean something. Yeah.
yeah, it should mean something, but I can't see it. just
It's
yet.
it's been around for some time, this corp. So I'm not sure if anybody considered it.
Okay, so let's thanks Dmitri again.